Hello, eCognition fans, eCognition users out there. Welcome to our webinar series. We're starting up after a bit of a break. Summer holidays came. We've been working hard on the software itself, but we're happy to be back into our regular webinar series. I hope you will all be able to hear me given the complications of home office and local internet connections out there. If you have issues, then just raise your hand or drop me a line in the questions dialog if you cannot hear me. My name is Keith Peterson. I'm the product manager of our Trimble eCognition software, and I'm really excited to have with me today Dr. Benjamin Robertson from Bergen University in Norway. He's been doing some exciting research here, as you can see at the title of our webinar, on the automated mapping of rock glaciers using a combination of deep learning and OBIA techniques within our eCognition developer software. Just an overview of what we're going to be talking about today. I'll give a brief introduction to the Trimble eCognition software for those of you that may be new to us in the audience today. And then I'll hand right over to Ben to talk about the project and the solution that he and his team of researchers came up with. We'll do some question and answers. Ben has asked me for those of you out there with questions, you can post those anytime. I'll talk about how we can interact within the webinar in just a minute, but we're going to save those questions for the end. He'd rather give his talk, and then we'll do more of an extensive question and answer, and then just a little stay tuned messaging from my side. First of all, eCognition, if there's anybody out there that hasn't used the software yet, no hard feelings. We'll get you caught up to speed, a real quick overview of what this powerful software does and where it can be used. First of all, the general idea around eCognition is to transform data into information. Traditionally, we have our real world out here. We can capture the real world with various sensors. So we have image data, we have elevation data, maybe in point cloud or raster format. And we can take that data historically or traditionally, you could say, and we do a manual analysis. So maybe if we think way back to the days of digitizing tables, we've come a long way now with GIS software, but still digitizing, manually extracting information from that, manually extracting individual features, doing change detection, object recognition. That was all done manually in order to transform this data into information. So the end goal was maybe a land cover map, impervious surface mapping, or maybe even an individual tree map. Where eCognition comes in is we are replacing that manual, those manual procedures for doing information extraction with automated tools, and eCognition essentially provides you with this toolbox. Okay. Now, there are some unique features within eCognition, one being the concept of data fusion and the ability to combine different data sets. So within eCognition, you can use, of course, your imagery, raster data. You can also use a vector data, but you can also include point cloud data. And this data can be combined into a single project environment, which gives us the strength of tapping into the attributes of those different data sets to better describe features that we are looking for. Okay, so we can combine image layers with point cloud layers and vector layers, and we can have those different types of data sets communicate with one another within a single project environment to create a more robust description of what we are looking at or looking for. Secondly, there's the concept of dynamic analysis and the development of rule sets. So as the name eCognition developer implies, it's a development environment. The users can construct these dynamic analysis routines or workflows, what we call rule sets in eCognition. And an example of such a rule set can be seen here on the left part of my screen. And this will allow for an automated workflow routine or semi-automated. The degree of automation is really up to the user. And what we are ultimately trying to do within this rule set is translate, say, how you as a human visualize your data, how you are interpreting something in your data into code that the computer can understand and of course then ultimately automate. All right, that being said, that's sort of eCognition within in a nutshell. Today, I'm really excited. I want to jump right in and hand the screen over to Ben. Hopefully he remembers to share his screen from the get-go. I apologize again. But first of all, Dr. Benjamin Robertson is coming to us today from Bergen, Norway. Hopefully his internet connection will be clean and clear. And just a bit about Ben. He is a physical geographer and really specializes in remote sensing and glaciology. He is come from the University of Wales at, and I'm probably going to mispronounce this, Ben, at Aberystwyth, and has also moved on to the University of Bergen in Norway. During his PhD work, he has concentrated extensively on inventorying debris-covered glaciers using object-based image analysis techniques, particularly looking at calculating volume changes. But over the last few years, he and a team of his researchers are also looking into these rock glaciers and identifying rock glaciers. And this work, up until maybe pre-COVID, has brought him all over the world, visiting some beautiful places in Norway, the European Alps, Himalayas, and Andes. So his research is looking at different environments, and I'm really excited to hear about the research he has been doing. And Ben, the floor is yours. I will just hand you the screen sharing.
There we go. Is that sharing?
I see everything nicely. And I will mute myself for everybody. Just one reminder, I did forget, you're on listen-only mode, but you can use the question dialogue to communicate with us. Please post your questions, and after Ben's presentation, we'll go in and we'll field those different questions together. All right, Ben, all yours.
Great. Well, thank you for the introduction. Fairly decent pronunciation of Aberystwyth as well, so that's a plus. And thank you for the opportunity of letting me present this work. So this is from a paper that we just had published a couple of weeks ago. And I want to start by saying that I'm not a computer scientist, so I have kind of come into using deep learning through eCognition. I'm quite experienced in using eCognition for object-based analysis. So deep learning really presented an opportunity in order to solve a problem for mapping rock glaciers. And actually, this image you can see here on the starting slide kind of shows the problem quite nicely. It shows, I'm not sure, you probably can't see my mouse, but anyway, you can see an active rock glacier here on the left with this typical morphology. We've got an inactive rock glacier on the right-hand part, and we've got stable ground surrounding it. And it's very easy for us just to look at the image and bring out for our brain to interpret where we've got an active rock glacier, but it's very hard for an algorithm or a classification to extract this using just image spectra. So this integration of using deep learning or AI within object-based image analysis is a way of solving this problem. And there we go. The stuff I'm going to be presenting today is based on this paper that I saw that this was linked to in the eCognition blog. So I'm not going to be going into all the, for example, the thresholds used or anything like that, but all of that is in the paper. So if you have specific comments about the methods, I would suggest you have a look here. Okay, so many semi-arid environments around the world, such as this is an area of Chile here, they actually don't have many glaciers in these mountains. So you can, for example, you can see one here. This is Tapado Glacier in the top right of the screen. But what it does have is it has a lot of rock glaciers. You can see many of these on the slopes surrounding here. And the rock glaciers also contain ice, so they can be important for water resources, particularly as the glaciers in many of these areas are retreating at quite high rates. That means that the rock glaciers could be significant water resources in the future. Many of these areas, such as in the arid Andes or Central Asia, are projected to have up to a 30% reduction in glacial runoff by the end of the century. So rock glaciers are likely to become more of an important resource and something that we should be able to identify, create inventories, and monitor. So that was kind of the stimulus for this work. Rock glaciers are a mixture of ice-rich sediments and debris. They are a less dynamic response. They have a less dynamic response to climate, and yeah, as such, they can potentially hold water for a longer time. They are also an indication that we have permafrost conditions, and if I just click here, maybe you can see the laser pointer. We can see some kind of the characteristics of a rock glacier here. So they have often this ridge and furrow morphology on their surface, and a sharp scarp surrounding the outside of them. They often form in talus or next to steep slopes. And the estimation of how important these are to local hydrology varies. So some catchments in the US, I've seen some estimates of up to 30%. In the case of Chile, the Elqui River, it's around up to 13%. Estimates range around that. So up to 13% of the annual stream flow for the Elqui River can potentially come from rock glaciers. And this is an area that doesn't receive much rain at all. It's semi-arid, it's desert environments. So if you look at an NDVI image of this area, you can see that all the cultivated areas along here are along the Elqui River. So how the rock glaciers are changing is quite important to monitor in order to understand how water resources could be in the future. So we need to be able to create up-to-date and accurate inventories. In the field, this is typically done by looking at the geomorphology. Here's a picture of me looking a little bit baked in the Chilean sun, and you can see here these ridges and furrows that I was showing on this previous diagram. So you can really see this pronounced morphology. Yeah, you can't really see as well, but you've also got these steep slopes as well. But from a remote sensing point of view, you can imagine that if you cannot see this morphology, then spectrally it's very hard to separate the rock glacier surface from the surrounding bedrock and the surrounding material. So let's have a look at what these look like from satellite images. And to start with, let's look at a 10-meter resolution image, Sentinel-2 image. This is an area on the Tibetan Plateau. And you can see at 10 meters resolution, it's actually pretty hard to see the surface morphology. It's actually quite hard to even draw a border of where this is. So this is in the Poiku catchment of Tibet. It becomes a little bit easier if we move to higher resolution data sets. So this is a 50 centimeter resolution image. Here we can start to see some flow structures and start to really see where the boundaries of the rock glacier could be. But such data, such as Pleiades, is really expensive, and it also has a limited coverage per scene. So you cannot really do wide-scale inventorying with that. So here's an example, the same one we saw at the start. This has got some more pronounced morphology, but even so, most of the rock glacier inventories have been conducted based on manual interpretation. So manually creating polygons, digitizing within GIS, sometimes based on additional data sets such as a LiDAR DM or some INSAR, but the vast majority of the work is manual. So in many cases, this is using Google Earth. So I showed how the resolution is quite important. So in order to get around the expense of using very high resolution imagery, many papers and many scientists have used Google Earth imagery in order to create these inventories. And as such, the analysis is restricted to the creation of polygons within the software. And then perhaps there could be some sort of post-processing in GIS afterwards, but it really is slow and manual work. And additionally, it's quite subjective. This is a paper from last year where the authors show the huge variety between how different people can interpret a rock glacier in different ways. So especially if you look on the right, you can see different outlines from 14 operators, and there's a huge amount of variation. So ideally, an automatic method would not only save us time, but it could be more objective as well. So in order to kind of tackle this, first of all, I'm just going to introduce how glaciers are typically mapped. I'm not saying rock glaciers are glaciers, but we can kind of learn from the methods. And on the left here, you can see a Sentinel-2 image. This is again an area in Tibet. On the right, you can see a SAR coherence dataset. So SAR coherence is based on 2 radar images, approximately 1 month apart. And then anything that has changed between these 2 images is going to have a low coherence, so it's going to have a dark pixel. Everything that stayed the same is going to have a bright pixel. So you can see we've got the debris-covered tongue here of the glacier, and this has got a very kind of strong signal in the SAR coherence. The clean ice is even easier to identify just because it has such a strong spectral signature in the near-infrared and the short-wave infrared parts of the electromagnetic spectrum. So it's quite robust and easy to map clean ice and debris-covered ice. But unfortunately, these methods that work really well over quite large areas do not translate for rock glaciers. Spectrally, they are quite hard to separate from the surrounding terrain. And then if we look at radar coherence, you can see on the right, the rock glaciers are simply just not moving at a fast enough rate in order to have any pattern of coherence. So sadly, these methods in the vast majority of cases cannot really be used for identifying rock glaciers. So then the question is, how can we automate the identification of rock glaciers and the creation of rock glacier inventories? So I'm just going to go through a couple of the methods that are currently used before I showcase the paper that we published. So to start with, you can use the idea that rock glaciers are generally flowing due to gravity. Of course, this only applies for an active rock glacier, but in such case, you can see that anywhere where we've got an active rock glacier, we have a displacement. Both these images are based on 8 years of data, so an image from 2012 and 2020, and then they've been co-registered together on a pixel basis. You have to really have high resolution data sets. They have to be auto-rectified very well in order for them to sit perfectly on top of each other in order to see something like this. And you can see that in areas of steep terrain, we still have problems with the auto-rectification. But nevertheless, this idea that rock glaciers are flowing is often used as a basis for creating inventories. So some of the papers that have looked at rock glaciers over large areas have used radar interferometry, or INSAR. So these are the same rock glaciers we'll be looking at quite a bit in this talk. And on the right, you can see the change in phase, so the interferogram of these rock glaciers. So this is based on TerraSAR X data. It's 11 days apart. And these different colored patterns here, these relate to the phase between the images. And you can see it does line up quite nicely. We can see where we've got rock glaciers flowing, where we have stable ground. But there are two problems with this. The first thing is, as a technique, INSAR is very sensitive to the direction that the satellite is looking into, the line of sight. So as such, if you have a rock glacier flowing around a corner, you would potentially not see the displacements over the whole landform. In some ways, you can get around this by using ascending and descending data, but it's still quite complicated. Also, you could have processes such as solid fluxion that are also causing displacement, but are not necessarily related to rock glaciers. But potentially the greatest limitation of this is that areas that are not flowing, so inactive rock glaciers, can still have significant amounts of ice. So this is a paper published last year using various geophysical methods, and they found that there can still be significant amount of ice in inactive rock glaciers. So therefore they can still be important for water resources and for monitoring. So the challenge therefore is not just to identify where we've got active rock glaciers, but to identify where we also have inactive rock glaciers. So this is the same feature we've seen a couple of times. And if I just show you, the next slide is going to show some surface velocities based on this 8 years of Pleiades data that you saw a couple of slides ago. And you can see quite nicely that we have a very active part here, but this portion on the right is really not doing anything. It's pretty much just sat there, but it still may contain large amounts of ice. So the challenge is, in order to train an algorithm to identify active rock glaciers, but also inactive rock glaciers. And this is why I turned to using deep learning in order to recognize the surface morphology. So we're trying to train an algorithm in order to look at an image in the same way our brain would interpret it and recognize these ridges and furrows on the surface, the steep slopes around it, and use that in order to predict which pixels contain an active rock glacier and which ones do not. So I'm not going to go into the ins and outs of how deep learning works, but to kind of explain it in a few slides, it comes down to pattern recognition and looking for patterns that recur again and again. So for example, it's often used for converting handwriting or spoken text into digital text. So in such a case, you may train an AI network to recognize an X or recognize an O. But the nice thing with working with deep learning or AI is it can work with situations such as this, where the data you're working with does not correspond exactly to your training data. And especially when we're working with things such as rock glaciers that can flow, they can transform, they can deform in different ways, this can be quite useful. So in such a case, the output of a deep learning classification is a probability heat map, where every pixel is given a value between 0 and 100%, depending on how sure the algorithm is that this given pixel belongs to an X or an O or a rock glacier. And in most cases, we're actually going to be somewhere in between. So I'll come back to this later, but this is how it's an advantage to use deep learning within an object-based framework, because then we can use morphology, we can use objects, we can use different things in order to classify our rock glaciers. And deep learning networks are typically made up of several different layers, where each layer has a different kernel size in order to look for different size patterns. And there's a lot of literature of how this can potentially be used, but I actually found surprisingly little on how it can be used on things such as rock glaciers and natural landforms. So my way of doing this was just using trial and error to kind of go through and see what kernel sizes produce the cleanest results. And I found that actually having several layers in the classification, but with very small kernel sizes, worked quite nicely. It produced a cleaner heat map, and it was able to resolve finer surface morphology features. There are probably people out there that know this a lot better than me, but at least that was my experience, and that's what I used in this paper. Now, in order to train a deep learning network, in order to recognize these patterns, you need a lot of data in order to train the different variations you can have in these patterns. So you may have noticed that when you're browsing the internet, Google will often pop up and ask you to identify all of the pictures that have got, for example, a statue or a car or a building in. And essentially what they're doing here is they are just making you train their algorithms and also giving you, you're giving them validation data. So this is how they want to train deep learning networks in order to, for example, classify Google Street View. Luckily, when it comes to geomorphology, we don't have to stoop so low, and we can use existing inventories and quaternary maps in order to train our classifiers. So as long as this data is spatial, we can put it into GIS, we can put it into eCognition, and then we can use that to train the deep learning in order to look for what textures it associates with, for example, a rock glacier. So for this study, we worked in two different areas. So the first one was this area in Chile I've been showing a few times. It's just to the east of the city of La Serena on the border with Argentina in the semi-arid Andes. So this area is called the Laguna catchment. I'll come back to that in a little bit. And then the second area that we tried it in was an area in the Himalayas on the Tibetan and Nepali border called the Poiku catchment. And these areas are kind of contrasting in some ways. So in Chile, we have a lot of rock glaciers. We only really have this one glacier here. It's very arid, so there aren't any lakes. But in Tibet, we have debris-covered ice, we have clean ice, we have lakes. So it's really a lot of different things that could potentially throw the algorithm. So the point was to try to train a method that will work in two quite contrasting areas. So let's look at the methods. I'm not going to go into these in all the detail. There's some pre-processing, creating the DMs example, but essentially using Sentinel-1, Sentinel-2 data, as well as some elevation data, combined with the existing inventories. In some cases, these were a bit out of date, so they were updated for a small area for training data. And we separated all of the polygons into training data and validation data. And then the deep learning network was trained on this and then applied, producing a probability heat map. And I think it is worth pointing out that many of the studies that use deep learning to map features such as rock glaciers or avalanche deposits, they typically stop here. They will produce a heat map. Sometimes they will segment that based on a fixed threshold into a Boolean layer where it's either, for example, rock glacier or not rock glacier. And sometimes this will work well, but the advantage of using this within OBIA is that you can add a lot more logic to your classifications. So let's have a look at this heat map, and then I will show you how the benefits of combining this with OBIA. So here's this same rock glacier that we saw in Tibet before. I should point out as well that this first classification results I'm showing you, this is based on just the Sentinel data. So later on, it was repeated using Pleiades data, but to start with, it's just based on Sentinel data. So this is what the Sentinel image looks like. Sorry, this laser pointer is going a bit crazy. I'm gonna switch it off. And then this is what the probability heat map looked like. So it's actually done a fairly good job, but there are a couple of things that if we would just take a fixed threshold value, it would not result in the cleanest outline. So for example, we've got really steep terrain back here. We've got some low probability heat map values that are surrounded by areas of the rock glacier. They all kind of have the same morphology. So perhaps this area, the morphology was less distinct but it probably is part of the rock glacier. But the deep learning algorithm has said that it's probably not. And then we've also got this sort of salt and pepper effect down here, resulting in a few isolated pixels. So by using object-based image analysis, we can conduct the post-processing in the same workflow. So we can segment the image by the morphology, so based on the slope and the curvature. Then we can assign objects to be rock glaciers based on a combination of this morphology as well as the heat map. And then we can filter and clean up our classification using a combination of the object size, its shape, and its contextual information. And lastly, this contextual information means that we can do things such as expand into neighboring objects if they share, for example, a similar slope or a similar spectral value. So by using this OBIA logic, we can increase the transferability of our method. So I think that is kind of the novel part of this method, is in one workflow combining the deep learning with the OBIA refinement. Probably, as this is for the eCognition community, you're probably familiar with these sorts of parameters, but essentially it was a 3-level segmentation performed to create objects that generally lined up with the morphology, and then a combination of the heat map, the slope, and the standard deviation of the slope, so really the roughness, were used to classify the rock glaciers. It was then cleaned up before the objects were merged, and there was some pixel-based smoothing. And the goal was to really make this as few steps as possible, because it was supposed to work over different regions. So the deep learning was the first stage, and then just a kind of quite simple cleanup operation afterwards. And when we do that, it produced outlines like this. So you can see that it's managed to map this area as part of the rock glacier, even if it has a low value. Still is going a little bit too far up into this steep slope, but it does stop here at least. And we've ignored these few isolated pixels. So the OBIA managed to actually produce an outline that can be used as an inventory. And in order to really kind of assess how well this worked, it's quite nice to compare with some field photos. So on the left here, you can see the probability heat map ranging between 0, which is in kind of the bluer colors, and 1 in the redder, more vibrant colors. So this is how sure the algorithm is that every pixel belongs to a rock glacier. The central column, you can see the Sentinel-2 image and the rock glacier inventory. So this is the kind of the manual inventory used for validation. And on the right, we've got 2 field photos. These should actually probably be swapped around. But the point I was making here is that where we've got areas with really pronounced surface morphology, such as here, this corresponds to A here, we get very high values in our heat map. While areas such as B, where we've got pretty flat morphology, actually you can't really see these ridges and furrows so well, there we have lower heat map values. So again, by combining this in OBIA, it means that we are not having strangely shaped outlines. We're allowed to use the morphology as well. So it's a huge advantage. So the heat map is really affected by the geomorphology. So let's have a look at some results. In total, of the 120 rock glaciers across both catchments, 108 of them were identified. In total, it was about 28% deviation in area as over the whole sample size, but individually there was a lot of variation. So here we can see the Chile study site on the left and the Tibetan one on the right. And generally the results were pretty comparable between the 2 study areas. The user accuracy, so the accuracy of every of how the inventory identified the rock glaciers in terms of false positives, for example, it was in the 60s, so it's okay, but there's definitely many cases where the rock glaciers have been overestimated or indeed underestimated. but the producer accuracies are a lot higher. So that means that we are identifying most of the rock glaciers in these catchments. So earlier on, we looked at different resolutions of image. So for a small area around here, we repeated the analysis using the Pleiades imagery, wanting to find out if we use higher resolution imagery with a greater spatial resolution, then will you get a better results? Will you be able to pick out finer surface morphologies? So this is the Pleiades imagery again, and when we do the heat map for the same rock glacier using this as the input instead of the Sentinel imagery, we get a heat map that looks like this. So there's definitely more detail around the margins. We're also getting more interesting information about the surface features, for example, smaller scale information about where we've got less pronounced morphology. But we are also getting a lot more false positives. We're getting perhaps bottoms of valleys or little areas where the texture is quite similar to that of a rock glacier, and therefore the heat map is being flagged up. So what we found is that when working with higher resolution imagery is that the producer accuracy doesn't really change at all. So it's not identifying more rock glaciers in the catchment, but the ones that it is identifying, it's generally mapping to a higher accuracy. So you can see these outlines here on the left. There's one interesting thing I wanted to point out in this figure, and that's this area with a red box up here. So the manual outlines show 3 separate different landforms here, yet the method mapped all of this as one rock glacier. And after inspecting this, we weren't really sure what is right. Perhaps the manual inventory should be changed in this case. We weren't sure if this was a periglacial, so a rock glacier geomorphology, if this was fluvial or glacial. So it could actually be that this is one greater landform, and perhaps the accuracy is a little bit better than reported here. But nevertheless, it's interesting, I think, to show that the producer accuracy doesn't really change much, but we can get greater user accuracies by using higher resolution imagery. So last couple of slides, I wanted to talk about future plans for this method. So as I was talking about the difference between active and inactive rock glaciers, using InSAR will be an interesting way of identifying not just which landforms are active and inactive, but which parts of a landform. So for example, we've got one rock glacier here where it has one side of it is flowing, but the other side is inactive. So perhaps by using interferometry over this area, we can identify training data for the morphology for an active and an inactive rock glacier instead of just training for all rock glaciers. So this is definitely a future plan to include this in the classification. And another bit of ongoing work is looking at validation with digital elevation model differencing, so looking at volume changes over time. And the reason this is interesting for one of the landforms I've chosen here is it's actually a hybrid landform. It contains clean ice up here, debris covered ice here, and a rock glacier section down here. So by looking at the volume changes, we can sort of see the boundary to the debris covered ice. So perhaps this is something else we can put into the classification to see how much the volume has changed over time and whether that can say something about the origin of these landforms. And in order to see very small scale changes, COVID permitting, we would like to perform some validation with drones as well. So this area you're looking at here is actually on the clean ice section of this landform, but it's looking at the formation of a feature called penitente. So it's these columns of ice you sometimes get in arid environments. So again, just using drones, perhaps we can get very detailed imagery. We can get velocities to see again the inactive areas, and this could potentially be put into the classifications to improve it in the future. So in conclusion, a combination of deep learning but integrated with object-based image analysis can be used to identify rock glaciers even with 10-meter resolution Sentinel imagery. Increasing the resolution does increase the user accuracy, but it doesn't increase the producer accuracy. So then this raises some question of, is it worth the extra expense of this imagery? And the nice thing about running this through eCognition is that we can have all of this as one workflow. So I actually tried running some deep learning through Python instead of eCognition, and it became quite complicated with the tiling, with the working with reference systems. So by doing this in eCognition, all of this was taken care of, and then the heat map could be directly manipulated as the next step. So it means for a pretty efficient workflow. And I know the accuracy of this method is not perfect, but it can still reduce the amount of time needed when creating rock glacier inventories. We have, in some ways, a baseline product that can be later refined for creating inventories. So that's everything I was going to say. So thank you for your attention, and if there are any questions, just let me know.
Yeah, Ben, thank you very much for the presentation. We can certainly get over into the Q&A session. I'll just grab the control and make sure I show my screen again this time. A number of questions have come in. I hope everybody can still hear me. And I'll just pick some off the top here. One of the questions that came in was concerning where you got the digital elevation model data. Was this derived from the Pleiades imagery?
It was. So for the Himalayas, there is an open source DM, an 8-meter DM that you can just download. But in order to be consistent between both study areas, because there's not something like this for Chile, we chose to generate our DMs from stereo imagery, so Pleiades imagery. So obviously this is a limitation because typically this data is not free. You can get it free from the European Space Agency if you are in Europe. So that's how we got this data. But yeah, it would be interesting to see if using this High Mountain Asia DM or some other national DMs could produce similar results. My experience as well is that the deep learning part of the workflow is really sensitive to no data values. So if you've got a DM where you've got some hole, which typically you find in, for example, this High Mountain Asia DM, that can really throw off the algorithm, either because it's looking at the patterns of the in the pixels. So if you suddenly go from a value of, say, 1,000 meters above sea level to just no data, perhaps it reads that as a 0, and then you've got a really high slope. I'm not 100% sure, but I found that having even slight holes or filled data was quite a problem for the algorithm. So in that case, it was best to use the Pleiades DM that we generated.
Interesting. Yeah, could consider running some types of smoothing or gap filling on those DMs, but you also risk losing some of maybe the original resolution effects.
Yeah, and especially when the morphology is really important here.
Yeah.
But yeah, it would be interesting to try.
Great. Another question came in, and it was regarding the methodology that you had. So I think you broke up the project into several parts, and the question was, what software did you use for the first part of this project? Was it also eCognition Developer? And I looked away at that point.
eCognition was used for the whole workflow. So the only things it wasn't used for was generating the DM. That was done in PCI Geomatica, and also just creating random points within the existing inventories to create training data. So I did that just in ArcGIS. There might be ways of doing that in eCognition as well. I found a way I could load in the whole shape files and use that as training data, but yeah, I'm not really sure. There could be better ways of loading the training data in, and maybe eCognition could be used more. But the whole classification was done in eCognition, from training to refinement to creating the outlines.
Great. Another question here on is whether you've worked with or considered and again, my lack of geological knowledge here, is relict rock glaciers.
It is something that it would be interesting to have a look at, but at least the motivation in this case was looking for landforms that could contain ice. But I'm sure it could be interesting as well to try to see if you can train an algorithm to identify those. That could definitely be interesting, but it's not something that we looked at in this case.
Okay. And then I guess returning to the DM question, do you feel as though that is really required for this type of analysis, or could you do this purely based on say the spectral values or the characteristics of the imagery that you have?
I think the DM is quite important, just because it's quite strong geomorphology around the edges of these landforms. So I did try without it when I was setting this up. I kind of started with very simple, just the multispectral layers, and then I added in the DM afterwards, and it did make a big improvement. You got a lot less false positives. For example, you've maybe got an avalanche deposit. Spectrally, it looks like a rock glacier, but the morphology is quite different when you look at the elevation data.
Great. And this one, I think when I was reading through the paper that you have, and I would really encourage people, after this to go read the paper that Ben had. You go into much more detail than can be done sometimes within an hour. But one of the things I believe you talked about in the paper was how maybe vegetation, and this listener is particularly interested in whether lichen cover or rock type affected the classification at all. And I know you discussed a little bit more about vegetation cover in your paper, but does this also go in that direction? How would that impact the results that you're getting?
Yeah, that's a good question. For example, in the European Alps, like in the Swiss Alps, you have rock glaciers that do have vegetation growing on them, or at least around the edges. So in that case, just looking at the NDVI or something can help. But in areas such as Chile, this is really like a building site. It's just a pile of debris everywhere. Nothing is stable in this landscape, so there's very, very little vegetation. So in that case, there isn't any vegetation, and the point was to try to make something that's transferable. So that's why I decided not to go in the direction of using things such as the NDVI, just so it can work in something like this. But on the flip side, for areas where you've got the no vegetation, it means that INSAR is going to work a lot better. So the INSAR works pretty nicely in arid areas, but then you've got no vegetation. So you kind of have one method that works well, one method that doesn't work in each setting.
Great. Another question here coming in concerning the input data. So you used in part the Sentinel data, so 10-meter resolution. I think you can answer this pretty easily. Can this method also be used for higher resolution, something less than 10-meter resolution? And since you are using the Pleiades, what was the resolution of that data set?
We used it at 2 meters resolution just because my computer couldn't handle the pan sharpened data set at 0.5 meter. But you can absolutely do it at higher spatial resolution, and I think that would be something really nice to do, just to see if you would do it over a large area, what extra information can you get out of it. And I think the extra textures you could see, that could really help in, for example, the active versus non-active rock glaciers.
The question came in here. I can take this one. It was, does eCognition actually utilize point clouds? And the answer is yes, absolutely. You can bring in point cloud data in LAS or LAZ formats, and you can work directly with point cloud features, or you can take those point clouds and do various rasterization techniques and create your own DEM within eCognition from those. Another question along these lines of point clouds that I was thinking of when you were showing some of the continuing ideas for the research was particularly with UAVs. Have you also considered LiDAR data sets, say a LiDAR payload on a UAV to look at some of these glacial structures?
Yeah, and I think with that, with the resolution you can get out of that, you could look at a lot finer scale landforms. So we found that a lot of the smaller rock glaciers, it was very hard to identify them just because you couldn't see any surface morphology at 10-meter resolution or even case 2 meters. So with LiDAR or with UAVs, you may be able to see a lot more.
Great. One question here is about the scalability. What about the scalability of the data sets while using deep learning? Did you find a great difference, say, moving that model from your deep learning model from the Sentinel to the Pleiades data set?
It was actually a bit of a challenge within the software. So also found that you couldn't have the same deep learning structure just because your computer just runs out of memory so quickly. So it could be, perhaps there's ways of getting around this, but so the resulting structure we have for the Pleiades imagery, it had to be slightly modified just because it had so many convolutional network layers on the high resolution data, it just you ran out of memory. So scaling was a problem.
Yeah, in general, when you're looking, my experience is when training these neural networks, they are, say, sensor. They can be very sensor specific. So particularly when you take a big leap from 10 meters to 2 meters or half a meter, there are going to be different types of characteristics going on because they're looking at some of the internal textures. So you may have to generate, most likely you'll have to generate 2 different types of models for this.
Yeah, so we tried to have the model as similar as possible, and it was very similar. The only difference was just had to have a slightly different structure. But then the OBIA part worked exactly the same. So once you've got a fairly decent heat map, the refinement steps were the same for both workflows.
Great. Just looking at a few others, we're starting to approach the end of our hour. There are some questions about whether you looked at the flow dynamics of the glacier in any of the analysis.
Yeah, there is some work going on by one of my colleagues looking at how the flow is changing over time. So yes, and I'm also doing some feature tracking. So this velocity data I showed over showing the active versus the inactive, this is something I'm working on now. So yeah, looking at velocities and how they're changing over time as well. So it's something we're looking at.
Okay. Another question came in here. I can also take this one as, would the deep learning workflow in eCognition work with point clouds? If it's sort of one of those, as we say in German, a Jein answers, a yes, no. You can take, currently we are using the Google TensorFlow library within eCognition, and at the moment this is restricted to our raster inputs. So if you're going to apply deep learning to point cloud data, you would first have to rasterize that, but that can be done directly within eCognition. We're actually doing quite a bit of this on some internal studies. So you could bring that in, rasterize a certain feature of your point cloud. Maybe it's the intensity, maybe it's purely the Z values of some return. And then on that rasterized result, then you could start running the deep learning on that. All right. That being said, I have a bit of business just to tidy up here. If we did not answer your question today, I apologize. but you can also reach out to us and follow up questions. You can send those to support@ecognition.com. This webinar has been recorded. We will make it available within the next 48 to 72 hours, depending on how fast we can get it downloaded and up into our YouTube channel, which brings me to the next slide here. So stay tuned. We have a number of eCognition events, happenings taking place here. And the next one would be the announcement for our October webinar. We're trying to get these up and running regularly again. And we're going to be doing one in October. It's going to be on timber cruising with eCognition, so looking at extracting individual trees from LiDAR data in combination with imagery and some of those attributes. The final date is still to be determined, so stay tuned. And where can you stay tuned and get up to date? If you didn't notice yet, the eCognition community is back. Yay. So you can join today, very easy to log in. You can just go to support.ecognition.com. We also make announcements on webinars and things that will be blasted there, and everybody who's following those threads in the eCognition community will be notified of that. We are also bringing more content to eCognition TV. So again, the webinar is recorded. We have a whole section within eCognition TV. You can see the URL here. On webinars, you can subscribe to our channel and get updates. We're going to be bringing back more of the deconstructed videos in the future here. So this will also be expanding as we move forward. And finally, stay up to date on our blog. So if maybe you saw the announcement to this webinar, we also have a great blog post on the research that Ben did. If anybody's looking for the references to the paper in my write-up on Ben's research, I say Ben and his team, that can be found in the eCognition blog. Again, URL is here. If you don't want to write down 3 of these URLs, then just remember one, it's ecognition.com, and our website connects the whole eCognition world. So from our website, you can get to the community, you can get to eCognition TV, you can get to webinar registrations, as well, of course, to the blog. And if you have any recommendations for future webinar topics, if there's something that you would like to see us do, then let us know. You can use the community as a perfect outlet for that. Let us know what type of material that you've always been looking for. If you have questions, even from today's webinar, post those in the eCognition community. Start discussions there, and Ben will either log in and answer, or we can field some of these questions as well. That being said, I'd like to thank everybody for attending. The hour's up. We'll keep it right in today. And I'd also like to thank Ben again for sharing this research, and hopefully we'll have you back in the future on some of the future projects that you'll be working on.
Yeah, definitely.
All right, then everybody enjoy the rest of your day, and we will say thank you. And if you do come, see you in October in our next webinar. It should be pretty fun, power hour, where we really dive deep into rule sets and the various functionality. So thank you, and hope to see you again. Take care. Have a great day.